Hi, good morning. My name is Don Pringle. I'm a physics teacher at Ferndale High School, which is up in the northwest corner of Washington State. I've been teaching physics for about 23 years now in the high school setting. My degree is in physics education. And earlier in my career, in the early 2000s, I was introduced to an instructional model called modeling instruction. And I've been asked by Dr. Palmquist to just take a couple of minutes and to put together a brief summary of what modeling is and how I use it in my classroom. Now, modeling has been around for a long time. It was introduced in the 90s, in the late 90s, developed at Arizona State University by a group of high school teachers and physics education researchers who were attempting to take a lot of wonderful information about the way that students construct basic understanding in physics and to develop that into a curriculum that could be deployed in a high school setting. A lot of reform physics curricula are developed to be deployed at the introductory collegiate level. And so the modeling physics instruction curriculum was, if I remember correctly, developed using a National Science Foundation grant with the intent of developing curriculum that could be used, as I said, by high school teachers with high school students. So the curriculum is fairly expansive and would cover an entire year of physics instruction. It begins with a unit looking at scientific thinking in experimental settings. It then goes on to constant velocity and then uniform acceleration. We then go into a basic force model and then deployment of that force model in a couple of different circumstances, including in Unit 6 in two-dimensional settings. Then towards the end of the curriculum, we explore energy and then circular motion, uniform circular motion, momentum later in Unit 9, okay? The modeling method really has two phases. In the first phase or stage, students are engaged in inquiry type experiences in the lab to develop the model, which is a combination of concepts, equations, ideas, interpretation of graphs and such that they then use to describe that little nugget of mechanics that we're focusing on. The four pieces of the model development include description, formulation, ramification, validation, and then stage 2, of course, students are developing the model. Okay, all right. So what I'm hoping to do, again, the presentation I'm sharing with you right now was something that I shared at a AAPT section meeting at Western Washington University a number of years ago. Okay, and so what I put together is supposed to last much longer than the couple of minutes that I've been given here by Dr. Palmquist. But let me just take a couple of nuggets out of this. So those of you that may not be familiar with modeling can at least have a taste of what modeling entails and how it's different from other ways of teaching high school physics. Okay, so I have built this presentation around Unit 2, which explores constant velocity. Now, interestingly, when I taught physics more traditionally, constant velocity was usually something that we discussed maybe in half of a class period, or maybe we took a full class period to discuss constant velocity, because in reality, the equations that are used to describe constant velocity are fairly straightforward. And a student can learn pretty quickly to take those equations, to pull them down, and to turn them into something that that they can just spit through equations pretty easily. Okay, sorry. But modeling is about more than students just being able to identify an equation and then just regurgitate or just sort of mechanically move through the process of grabbing numbers and throwing them into an equation. The intent is that students through their experiences will develop a deep understanding of the basic concept that they're looking at. And it turns out that constant velocity, the constant velocity model, is one of the pillars of the students' developing understanding of really all of mechanics, okay? This is Unit 2. In Unit 3, they look at uniform acceleration, which turns out to be the other pillar, of course, as far as describing motion. And then the piece that links those two is the force model, where students learn that when the force is acting on an object or balance, then of course we have constant velocity, and that's where the constant velocity model is applied. And then when the force is acting on the object or unbalanced, of course, that's the uniform acceleration, that's the unbalanced force model. And when we use the uniform acceleration model is developed in Unit 3, okay? So here are the basic objectives for this unit, okay? I've left them up on the screen much longer than you probably needed. But let me just walk you through the process that students use, and it's a lot of fun, that students use in the development of the model. So most of the model development begins first with the teacher demonstration. So you see a picture of me standing in my classroom, and I'm holding up one of those constant velocity buggies that are readily available, and probably most of us have. In the demonstration, what I do is I turn the buggy on and I set it on the table, and I just, in silence, just allow the students to observe it move across the front of my demonstration table. I do that a couple of times, and the students, of course, are horribly unimpressed because all it is a buggy moving across the table. I then ask the students, what about that thing that they've just observed is measurable, right? What could they measure from that? And that usually brings up a huge list of things from the students, suggestions about things that we could measure. And so you'll see on the board behind me examples of things that the kids, and again, this is all coming from the students, suggest that would be measurable. So speed, distance, time, acceleration, tow capacity, the angle of the surface at, the horsepower of the buggy, and all these different things. And it's very important in this initial phase that there is no wrong answer, that anything that's suggested goes up on the board, okay? We then try to narrow this discussion down a little bit, and I ask them now, after they think about everything that could be measured, what in that list is something that we could actually measure in the lab? What in the lab do we have the tools for that would allow us to make those measurements? And so we're looking for variables that we can actually measure. So for instance, I don't have a device that could measure the torque output of, or the torque provided by the motor. So we scratch that off the list. The tow capacity, we scratch off the list. I, at this point, and the modeling instructor at this point would guide the discussion Socratically a little bit to eliminate some variables that are not going to be helpful in us developing our model. The intention is to get to the point where the students identify 2 or 3 variables that appear to be related to each other, okay? And so in this case, I'm hoping that I can skillfully and Socratically direct them to want to explore the relationship between the position of a buggy and the clock reading or the time on a stopwatch, okay? After the students have come to that conclusion, they are then cut loose in the lab. And in the lab, they basically do a free inquiry investigation. So this takes quite a bit of time. It's a time-consuming process at the very beginning, but without taking the time and allowing them to really explore and to make mistakes in the collecting of the data and the information, and then the representing of that information graphically, the students don't really get a chance to mentally grapple with what we're exploring, okay? And so you'll see down there on the ground or on the picture different examples of how the students are choosing to perform the experiment. The one that's in the bottom left is a student has made the choice to, in this case, manipulate the clock reading. So every 1 second, the student would be calling out Mark, and then another student using masking tape would be marking the position of the buggy. The students then use software, and they don't have to use software because this is a simple relationship, but they then use software to put the data into the software, of course, and then to generate a graph. Here is an example of a student that's done it by hand. And so you'll see their data table of position versus time. And then here we have on the graph. And on the y-axis in the graph, you'll see they've graphed position, and in the x-axis they've graphed time. Okay. So now that they have generated that, the next step in the modeling process is for them basically to report out the results and for us to have a Socratic dialogue around those results and the implication, the meaning of those results. Okay. Meanwhile, I, as the teacher, have been going amongst all of the groups and asking important questions with the intent of guiding their thinking towards collecting good solid data, towards graphing useful relationships so that we can have a productive whole group discussion after the lab portion is complete. Okay. And so here's a picture of my students doing the reporting out piece. This is where they use whiteboards, and on the whiteboards they put two important things. So number one, they put the main graph that shows the relationship between the two variables that we as a class agreed to go and investigate. And then the boards are a little too small, so you can't see it well, but another important piece, and the board that's in the middle, right underneath the eyewash station, you can see it in the lower right-hand corner, is an equation that the students have written using, it's essentially linear regression, but because this relationship turned out to be linear, they're just using y equals mx plus b to turn that into, well, we'll see in a minute, but they're basically going to be developing the model of position is equal to the velocity times the time. Okay, that's what we're working them towards, is understanding that relationship. So from this graph and this particular group, so you'll see closely here, they've as is instructed in the lab, they've graphed the motion of two buggies. The first buggy, which is represented by the line with the positive slope, the students kind of came up with on their own. The second one, that's scenario number 2, and they have to come to me and I give them scenario number 2. So for the case of this buggy, scenario number 2 would have been something like, okay, place the second buggy at position 3 meters, but I want you to have it go in the opposite direction. And so they go and they do that. Okay. You'll see up in the upper right-hand corner of this particular board, those are the equations that they've written, describing each of those lines. P representing position. The next number in there is the slope of the line. And you notice the slope for buggy number 1 is positive, whereas the slope for buggy number 2 is negative. And then there is a y-intercept included. And of course, at this point, I'm letting the students have their head about the units that they're using. You see this group is using inches per second. Other groups use centimeters, other groups use meters, and that's not particularly relevant at this stage, though I do point them towards metric and everything in standard units of meters, and et cetera, a little bit later. Okay, the next step is through the course of our Socratic dialogue that we'll have around each of these boards. There are a couple of important pieces that need to fall out of that discussion. Among those important pieces, they need to have a deep understanding of what the slope of that line means in this particular example, that the slope of the line describes two things. It describes how fast the buggy's moving, and it also describes the direction that the buggy is moving. And for instance, P1 and P2 are both traveling roughly at very similar speeds, okay? But P2 is heading in the opposite direction. And they learn to look at that equation that they developed and to recognize those important components, okay? So the slope, the magnitude of the slope, the students learn to articulate. It describes how fast, and then the sign of the slope describes the direction. And then the y-intercept they learn to describe gives us the starting position, or lets us know what the initial position of the buggy is, okay? Again, at this point, they have not been introduced to the term velocity. They really haven't been introduced to, aside from understanding it's just a marking on a ruler position and things like that. Those definitions come out of these whiteboard discussions as we're looking at these pieces, okay? All right, so there are 3 pieces of the constant velocity model that students are working on at this point. So they're working on a verbal model, which means the students can describe the motion of their buggy. A graphical model, meaning that they can use a graph to describe the position versus time graph to describe the motion of their buggy. Through the course of this unit, we also introduced the velocity versus time graph, which for each of these buggies would just be a horizontal line. But that comes a little bit later in this particular unit, in Unit 2. And the final piece is they're also receiving a mathematical model. So they understand that the slope of that line articulates, during this discussion, we introduced the term velocity, describes the velocity of the buggy, and then they get this generalized equation that's on the bottom of the slide. The final position equals velocity times time plus the initial position, which can describe the position of any buggy that's moving with a constant velocity, as long as we know the velocity, how long it's been moving, and where it started. Okay, after students have had this experience in the lab, which I have 90-minute periods, and these 90-minute blocks, these 90-minute periods, this particular experience that I've just described to you would probably take 2 of those periods. At the end of those periods, the students then go work in small groups on a series of, the kids consider them worksheets, but they're not really worksheets. What they are is a small collection of scenarios that the students analyze in small groups, and then following, so here's an example, okay? So following the group analyzing these scenarios, we then get together and have whiteboard discussions around each of these scenarios. So here is the first question from one of the first worksheets that the students look at after they've done this lab. And so they're presented with the position versus time graph for 2 bicyclists, cyclist A and cyclist B. And then part A, do the cyclists start at the same point? How do you know? If not, which is ahead? Okay. During the whiteboard discussions, students are asked by me, but also it's intended for this to be a Socratic experience. So as students are working on these, I go around and I allow incorrect answers to persist on the worksheets and on the whiteboards, so that when students get up, we can have discussions around those. And this takes quite a bit of work to develop an environment where students feel comfortable being wrong. And for some kids, that's really hard to get up and to not know if their whiteboard is 100% correct. But, it could have some wrong information on there. But for them to get up there and they present the board to the class, and the students ask questions. I will ask some questions, but the intent is for us to have a discussion around each of these whiteboards. And then through these discussions, the important key concepts of the unit are taught and reinforced, okay? So you'll notice there hasn't been a point in the instruction, except at the very beginning, where I, as the instructor, am standing in front of the class, lecturing on equations and doing practice problems, okay? That's not a part of how instruction is given in modeling. After students have worked through 2 or 3, if I remember correctly, there might be a 4th experience with the worksheets and the whiteboarding and all of that. We then do a lab practical. And so the buggy lab practical is an opportunity for them to deploy their new constant velocity model in a real life scenario where they have the opportunity to use nature, so to speak, to test the prediction of the model. And so students, in essence, will take 2 buggies, and I've modified one of them so it only has a single battery in it, but they don't know that. So they'll have a fast buggy and a slow buggy. They come to me, I tell them where the two buggies need to start and what direction they're heading. So the buggies will either head towards each other, or we'll have a slow buggy being chased by a fast buggy, and the slow buggy starts ahead. But what they need to do is use their model. Okay, and again, they're getting very little instruction from me to predict the location where the two buggies will collide. And to sweeten the pot a little bit, their grade on this is determined by their performance a little bit. There is a performance component. So if they're within 10 centimeters, then they get full credit. And if they're outside of that, then they lose. It's a token amount of points, but it's enough to motivate the students. Because it's a lab practical, the students don't actually get to test their prediction. The testing is done in front of the entire class, and it's really fun. They're like cheering for each other's buggies and things like that. But they do get the buggies initially, where they're allowed to, they take the buggies and they make whatever measurements they feel they need to around the buggies. And then they have to turn the buggies in. They then go use their model to predict where they're going to collide. And then we do it as a class. One group at a time comes up and they crash their buggies. And 90% of the time, the students are spot on in their predictions. So the interesting piece of this for me is that some groups will choose to use the mathematical model that they've developed. They'll use the equations to predict the point where they collide. Others will use the graphical model. They will figure out the velocity of each of the buggies, and then they will graph them, and that point where the lines intersect, the two lines for the buggies, the position time graphs for the buggies intersect. They understand that's where they collide. And so they develop a very deep understanding of constant velocity and how to describe constant velocity. Some people struggle a little bit with modeling because it takes quite a bit of time. What I just described will take probably 3 full weeks of instruction. And you think, oh my gosh, you're going to take 3 weeks to cover instruction, whereas I, in my classroom, get it done in a half a day. I would argue that the difference is that, of course, at the end of that 3 weeks, my students deeply understand a couple of things. They deeply understand constant velocity, but they also deeply understand how to take information that they've gathered in the lab, and they develop tools that they can use to interpret that information and then to use it to make predictions. And so we use this process to study uniform acceleration. We use this process to understand balanced and unbalanced forces. We use the same process, this modeling process, to understand the interactions that lead to a conservation of momentum in collisions. And so it's a very powerful way to teach. If we were to take general physics and to make it into a pie, I cover maybe 1/3 of that pie with my general physics students. And I also use modeling to develop some of the instruction in my Central Washington University physics course that I teach at Ferndale High School also. And even though it takes quite a bit of time to develop the instruction, I have found that the students deeply understand it, and that the time that I lose in using modeling early in the year is more than made up for at the end, when we have to cook through some other concepts pretty quickly. I don't have to worry about whether or not students have a deep understanding of the basic material. Okay. All right. So if you're interested in learning more about modeling, the website at the top, modeling.asu.edu, is the original modeling website where all the modeling materials used to be posted. The NSF grant has expired. It expired quite some time ago, and ASU continued to maintain the site. I don't believe they do that anymore. But there is now a professional organization called the American Modeling Teachers Association that I believe now holds the materials, and they may even hold the copyright to the materials. And so you can go to their website and get more information about modeling. They hold workshops, and they're not free, but they do hold workshops where you can go and be trained in the modeling materials and get access to the modeling curriculum. I spent 2 full summers in Phoenix, which was a horrible time to be in Phoenix. I did this in the summer of 2003 and the summer of 2004. Where I went down to Arizona State University and was trained underneath the National Science Foundation grant by some of the teachers and the professors that were the originators of modeling. Okay, so I hope this was helpful information. It was probably a little bit longer than Dr. Palmquist really wanted it to be. But again, I hope it's helpful. Okay, all right, take care, everyone.